Thank you for your interest in my research statement. I am a theoretical condensed matter physicist and a postdoc in the University of Maryland at College Park under Shankar Dasarma's supervision. Now I'm looking for a long-term academic job. In this video, I'm going to present my past and current and future research. There are two major directions of my research in condensed matter physics. First, topological state of matters. Second, Majohn fermion in condensed matter physics. I am also interested in any direction to fundamental physics topics. First, let me talk about topological state of matters. Ching-Kai Chiu, Jeffrey Thiel, Andrea Snyder, and I spent 2 years in writing an important article entitled Classification of Topological Quantum Matter with Symmetries. In August 2016, this article was published in Review of Modern Physics. Let me talk a little bit about the history of a topological state of matters. The story started from the 80s. First, integer quantum Hall effect was observed by von Klinsing in 1980. This breakthrough of quantized Hall conductance was honored by Nobel Prize in 1985. Dulles and his collaborators found the quantized Hall conductance can be realized as integer topological invariant. Now we call it KKN number. It was so that quantized Hall conductance always need present of a magnetic field. Haldane showed in 1988 integer Hall effect can be realized in absence of a magnetic field. We call it chain insulator now. Their works opened the door of the topological state of matter. In 2016, Dulles and Haldane received Nobel Prize in Physics. 20 years later, this field started to grow rapidly after the discovery of two-dimensional topological insulators. Many exotic topological phases have been discovered in the experiment. Three-dimensional topological insulators, chain insulators, Dirac semi-metals, and wild semi-metals. So our review paper provides a clear picture to unify those concepts of a topological state of matter accumulated over 30 years. In the following, I am going to show why I have this background to write RMP. My topological career started when I was in the graduate school of Urbana-Champaign. I studied the tenfold classification of a topological insulator and superconductor with my thesis advisor Michael Stone in Urbana-Champaign. After tenfold classification, I was Hong Yao. Ching-Kai Chiu expanded the classification to the refraction symmetry, topological insulator, and superconductor. This article has reached 100 citations since 2013. When I was a Max Planck UBC postdoc fellow, I began to collaborate with Andrea Snyder in Max Planck. I have extended the classification to refraction symmetric topological semi-metals and nodal superconductors. This classification is able to predict a new topological semi-metal and a nodal superconductor other than YO and Dirac semi-metals. Andrea and I are looking for material realization for topological semi-metal in our classification. We found calcium phosphide compound is one of a topological nodal line material protected by refraction symmetry. I am also working with Zahid Hassan group in Princeton. We found lead tantalum diselenide and thallium tantalum diselenide are also these exotic topological nodal line materials. Furthermore, we have extended material hunting to new topological crystalline insulator. We are studying a family of anti-perovskite materials as a refractional symmetric topological insulator, which are one type of a crystallized insulator that possess exotic type 2 Dirac surface state exhibit different physical response from the normal Dirac state. Back to my graduate school, I was working on Majohn fermions in the heterostructure of N-wave superconductor and topological insulator with Tyler Hughes. This heterostructure is one of the promised platforms to realize Majohn fermions. This work, we successfully predicted the size of Majohn fermions, is consistent with experimental observation done by Shanghai Jiao Tong University. After moving to the University of British Columbia for postdoc, I have studied Majohn braiding with mutual friends. Typically, the braiding always occurs in 2D. Surprisingly, the braiding can be achieved in 1D by sacrificing topological protection. My interest has been extended to Majohn in tiling systems. there are two directions. First, I am interested in topological superconducting system without U1 symmetry breaking. That is, without using mean field approach, the attractive interaction still stays. The reason to study this is that I believe if we put topological superconducting in particle number conserved box, the Mahjong physics won't change. So what is Mahjong fermion in many-body wave function with U1 symmetry preserving? This is an important question to fully understand Mahjong fermion. Second, in pure Mahjong fermion system, we study only full Mahjong fermion interaction instead of regular fermion interactions. The reason we study this interacting system is that a realistic platform can be realized. That is the hierarchical structure of a topological insulator and a superconductor. Now I am at the University of Maryland. I am into the fundamental part of Mahjong fermion physics by studying superconducting proximity effect in the heterostructure. Recently, there was a discovery of Mahjong fermions in Coulomb blockade narrow wire. The article was published in Nature journal. Under Dasama's supervision, I have tried almost all of the narrow wire scenarios possessing Mahjong fermions. Our results are inconsistent with the experimental data. It is a work-in-progress project, but it is unlikely the Mahjong fermion appear in their narrow wire. Let me first talk about my review article in Review of Modern Physics. Basically, for non-interacting systems, we have included almost all of the topological phases in this table and the extension of this table. D indicates spatial dimension, T represents time reversal symmetry, C represents particle symmetry, S is chiral symmetry. 0 indicates non-symmetry, non-zero labels indicate system preserve less symmetry. These are symmetry class labels. In our RMP paper, we first talk about tenfold classification of a topological insulator and a superconductor. The reason it's called tenfold is there are 10 symmetry classes. Integer quantum Hall effect is one of well-known cases. It is in class A in 2D and has integer chain number labeled by Z describing the topology. Another example is the time reversal topological insulator in class A2 in 2D, protected by Z2 topological invariant. Second, we introduce refraction symmetry and provide the important classification of refraction symmetric topological insulator and superconductors. A crystallized topological insulator is one of the examples. Third, we move to the bulk Kepler systems. We provide the classification of topological semi-metals and nodal superconductors with and without refraction symmetry. The important examples are Weyl and Dirac semi-metals. Last but not least, we also review topological Kepler modes in defects and the current status of topological phases with interactions. In the following, I am going to talk about my past and current research, which is foundation and extension of this RMP paper. The tenfold classification was proposed by Ching-Kai Chiu, Andreas Snyder, Kitab, and their co-workers. In my graduate school, I worked with my thesis advisor at Michael Stone and used a simple way to understand this tenfold classification by studying Dirac Hamiltonian and used mathematical tool Cliff Algebra. After I developed the technique of the Dirac Hamiltonian method, I have done two new important classifications of the topological phases, and further used topological invariant method to confirm my result. First classification is the refraction symmetric topological insulator and superconductors. The second one is the topological semi-metal and nodal superconductors, without and with refraction symmetries. The detail of this classification will be discussed later. Currently, with my collaborators, I am working on the complete classification of topological insulator and superconductor for all possible space groups as a long-term project. One of my important works is the classification of refraction symmetric topological insulator and superconductors. I was inspired by the prediction and observation of a topological crystallized insulator. This is of course in this table. That is this topological crystallized insulator, which is a three-dimensional refraction symmetric topological insulator. It's characterized by mirror chain number MZ here. It turns out this is starting point of refractional topological phases. As you can see in this table, there are more undiscovered refractional topological phases. Our classifications show all possible topological phases protected by refraction symmetry. Topological semi-metal is also an exciting field in condensed matter physics. Andreas and I provided a simple classification table for bulk Kepler system. Classification depends on codimension P, which is a spatial dimension D subtracted by the dimension of Fermi surfaces. For example, for wild semi-metal, spatial dimension is 3, and Fermi surface dimension should be 0 because it's wild point. So codimension should be 3. In this case, we consider Fermi surface at hygiene points, in red color as shown in the figure. This classification is one-dimensional right-shift from the temporal classification. Not zero labels in the table show robust Fermi surface protected by topology. For example, the arrow indicates wild semi-metal. The variants indicate multiple wild points are stable against disorder. The classification is different when Fermi surfaces are located of high symmetry points. This figure shows Fermi surfaces in red color are of high symmetry points. Classification is one-dimensional left shift from the temporal classification. While semi-metal pointed by the arrows are protected by the invariant, the dashed lines are related with the hidden topological invariant. In 2015, the first wild semi-metal tantalum arsenide was discovered. Its wild points are located of high symmetry point. Similarly, when refraction symmetry is introduced, we can have the classification of refraction symmetric topological semi-metals and nodal superconductors. The classification for Fermi surface at high symmetry points within mirror planes is one-dimensional right shift from temporal table. The classification for Fermi surfaces of high symmetry points within mirror plane is one-dimensional left shift from temporal table. The observation of topological nodal lines in lead tantalum dicyanide is one of the predictions in our classification. For nodal line, the spatial dimension is 3, and Fermi surface dimension is 1, so we have a codimension is 2. There are no symmetry except for refraction symmetry, so we have a symmetry class is A, and this classify the non-trivial invariant NZ. Like wild points, the nodal lines protected by the topology are robust. We believe topological nodal lines might be the next trend after wild semi-metals. Except for the classifications, I am working on materialization for topological phases. Calcium phosphide is another candidate of topological 9-node semi-metal. We show this 9-node, which is a ring, is protected by the difference between the refraction numbers. Furthermore, we provide a comprehensive way to define topological invariant protected nodal lines. Physicists are using our definition to check topological nodal lines semi-metal. The realization of exotic topological crystallized insulators is one of my interests. We found calcium lead oxide is a topological crystallized insulator possessing exotic two-dimensional Dirac surface states. The angle of a Dirac cone is over-tilted. We call it type 2 Dirac surface state. The red arrow point here is type 2 Dirac point. Although types 2, 3D wild semi-metal have been observed, our paper is the first proposal of a type 2 2D Dirac surface state. These exotic states have electron and pole pockets and exhibit Van Hoff singularities, completely different from the normal Dirac surface state. Now, I would like to shift the gears and talk about Marchand fermion in condensed matter. I have studied two possible experimental setups of Marchand fermions. First, Marchand fermions are in the vortex ends of the topological insulator and the superconductor proximity heterostructures. This heterostructure was first proposed by Fu and Ken. We investigated how the vortex size of magnetic flux affects the energy of Marchand fermion in this setup. This figure shows the distribution of Marchand fermion in different vortex sizes of the magnetic flux. It turns out that when size is too small, smaller than one blockhead, Marchand fermions at top and bottom couple, as shown in this figure. The Marchand fermion penetrate the bulk to couple. The energy of Marchand fermion is not zero now. So to have zero energy, the size of vortex should be big enough. This figure shows when vortex size increase, Marchand fermions decouple and the energy is reduced to zero. Lambda is the vortex size of magnetic flux. These figures show that when vortex size increase, Magellan modes at the top and bottom are separated. Secondly, we consider the setup of superconducting doped topological insulators. Similarly, the Magellan fermion modes are in the vortex ends. Our study is slightly different from the original study. We consider additional trivial bands. It turns out the trivial bands stabilize the Magellan modes. The figure shows that the topological region of a chemical potential with trivial bands much larger than the original model. This is the original model. This is the model with the trivial band. The more larger topological region, the more stable Magellan fermions. We have discussed the hierarchical structure of a topological insulator and superconductor can host Magellan fermions on top of a topological insulator. Now we take one step back and ask a basic question how superconductivity is induced through proximity effect. The superconductive proximity effect induces two distinct quantities, spectral gap and pairing. First, spectral gap is the gap in BGG Hamiltonian. Presence of Magellan fermion relies on this gap. Without this gap, we cannot see the Magellan fermion because the topological insulator surface is just a normal metal. The pairing correlation is related with Cooper pairing, so it's nothing to do with Magellan fermion. The corresponding physical quantity of this Cooper pairing or correlation is supercurrent. My result shows that the criterion to have non-zero induced pairing correlation, the non-superconducting film, which is topological insulator, the momentum state must have zero energy. The figures show that the peak of the pairing correlation in topological region are located at zero energy momentum state. Furthermore, the topological insulator possesses strong spin-off coupling, which breaks SU2 symmetry in spin. It leads the equal strength of AAA and single-A pairing. Let's talk about spectral gap. As shown in the figure of the topological spectrum, we choose chemical potential close to the bottom of the bulk band. Therefore, the thin field of a topological insulator should be insulating. The green line of the exponential decay fits perfectly with the gap in the insulator region. The thick field is metallic. The red line of 1 over L cubed is also fit perfectly the gap in the metallic region. Hence, the induced spectral gap on top of the surface of metallic non-superconducting film exhibits 1 over L cubed decay, whereas the gap exhibits exponential decay for the insulator. However, to host Magellan fermion on top surface, we expect the topological insulator film should be truly insulating. Hence, due to the rapid decay of the induced gap, the film should be thin enough for strong induced gap. Unfortunately, the film is too thin. Magellan fermion on the top and bottom of the film hybridized, then Magellan fermion just vanish. The energy just disappear. I'm also working on braiding protocol of Magellan fermion systems. Our recent studies show it is possible to exchange Magellan fermion in strictly one-dimensional structures. We propose two possible protocols. First, it is one-dimensional Kitaev model. This is the topological region. A Magellan mode at each end of a topological chain. We move the pi domain wall from one end to the other end. Our recent paper shows that these two Magellan modes can exchange with some fine-tuning. Furthermore, we consider a more feasible setup, Magellan-Joseph junction. Magellan mode gamma 1 and gamma 2 at the end of a topological superconductor. The exchange can take place when we increase the magnetic flux through the ring, and an order-pair interface of half side of wire vary from 0 to 2 pi. Here's my future plan. With my collaborators, I am planning to completely classify the topological insulator and superconductor for all space groups. There are 17 space groups in 2D, 230 space groups in 3D, so it's gonna be a long-term and a big project. Second, people know space group and magnetic space group. Magnetic space group is related with the time reversal symmetry. So now I consider other symmetry to generate a new type of space group. Third, I will keep working on Magellan fermion realization and verification. Most of my studies are related to non-intacting system. So right now I would like to look at the topological order in Magellan fermion intacting system now. I'm also interested in any interesting fundamental physics projects and ideas. Thanks for watching this video. Ciao.